Welcome to Microservices Interview Masterclass. In this video, we answer most 18 common microservices interview questions you will face as a senior or staff backend engineer. We cover 5 pillars: foundations, communication, resilience, distributed work, and operations. These are the exact topics that separate passing candidates from the ones who get the offer. Let's get into it. Here is the map: 5 pillars, 18 questions. Foundations: what microservices are, when to use them, and what you are signing up for when you do. Communication: how services talk to each other and how you protect that conversation. Resilience: what happens when things fail, and in distributed systems, things always fail. Don't you ever forget that. Distributed work: this is how you coordinate transactions, events, and data across service boundaries without a two-phase commit. Operations: how you observe, secure, and run a microservice fleet in a production. By the end, you have a mental model that lets you answer any variant of these questions on the spot. Question 1. What are microservices? Microservices are intellectual style where an application is built as a collection of small, independent services, each responsible for specific business capability. Each service runs its own process, deploys independently, and communicates over a network. The keyword is independent. For example, independent deployment, scaling, failure. Everything is independent. That independence is both the benefit and the cost. Question 2. Monolith versus microservices. A monolith is a single deployment unit. One code base, one process. Fast to build for a small team, simple to test and operate. The correct default for most projects. A modular monolith keeps the clear module boundaries but runs in a single process. You get separation of concerns without network overhead. This is the step most teams skip when they should not. Microservices take that module boundary and enforce it with a network call. Now every interaction is potential failure. Deployment and scaling become per service. That's the trade-off. Independent everything at the cost of distributed system complexity. The interview answer is monolith is not legacy. It is the right default. Microservices earn their complexity at scale. Benefits and challenges. Independent deployments: you change one service without touching the rest. Independent scaling: you scale the services that need it, not the whole application. Technological flexibility: each service can use their best tool for its job. Fault isolation: a failing service does not bring everything down. Team autonomy: each team owns and ships its bounded context. Those are key benefits. But what about main challenges? Distributed system complexity. Network failures, latency, and partial failures are now your problem to solve. Second, data consistency. There is no single AC transaction across service boundaries. Think about it. Third, operational overhead. Service discovery, load balancing, distributed tracing, and per service CI/CD pipelines. And testing complexity. Integration tests are contract tests are significantly harder than unit tests in a monolith. The interview answer will be every benefit comes with a corresponding cost. Name them both. Candidates who only list the benefits are not senior. Question 5. How do services communicate? Few modes. Synchronous, HTTP or gRPC. You send a request and wait for a response. Tight temporal coupling. Both services must be available at the same time. Use this method when you need an answer immediately. Asynchronous, message queues like Kafka or RabbitMQ. Fire and forget. The producer does not wait. The message ID is durable. If the consumer is down, it waits. Decouples availability and improves resilience. Use this when you can afford eventual processing and need to decouple service uptime. Question 6. What is an API gateway? The single entry point in front of all your services. It handles request routing, authentication, rate limiting, SSL termination, and response aggregation. It is also where the backend for front-end pattern lives, aggregating multiple downstream calls into a single facing response. Without an API gateway, every client manages service discovery and authentication itself. That is a complexity you do not want to in a public interface. Question 7. Service discovery. Services find each other through a registry. Instances register on a start and the registers on a stop. Clients query the registry, either directly in client-side discovery or via a load balancer in server-side discovery. Console and Vertica are common registries. This is how you avoid hard-coded IP addresses in a fleet that scales dynamically. Question 8. The circuit breaker. When a downstream service starts failing, do not keep hammering it. The circuit breaker monitors failure rate. Once the threshold is crossed, It opens the circuit. Requests fail fast without touching the downstream service. After a timeout, it enters half open and probes with one request. Success closes the circuit. Failure keeps it open. Question 17. Bulkhead. Borrowed from the ship design, isolate your resource pools, thread pools, connection pools, per dependency. If one downstream service hangs and exhausts its pool, the other dependencies are unaffected. The circuit breaker stop calls after failure is detected. The bulkhead prevents a slow dependency from consuming all resources before failure is detected. Use them both. The Saga pattern. Distributed transactions are impossible with a single ACID boundary across services. Saga solved this by breaking the transaction into a sequence of local transactions. Each step publishes an event that triggers the next. If any step fails, compensating transactions undo the work already done. Two styles. Choreography. Services react to each other events. No central coordinator. Orchestration. A central Saga orchestrator tells each service what to do and handles compensation. Choreography is looser but harder to trace. Orchestration is more visible but introduces a coordination bottleneck. Question 18. Why does idempotency matter? In distributed systems, messages are retired and retried. Networks fail, timeouts happen, at least once delivery is realistically guaranteed. An idempotent operation produces the same result no matter how many times you call it. Combined with the at least once delivery, you achieve effectively once semantics. Without idempotency, retries cause double charges, duplicate records, and data corruption. Implement it with an idempotency key, a unique identifier per request or event. Store processed keys, return the original results for duplicates. Orchestration versus choreography. In orchestration, a central coordinator tells each service what to do. This flow is visible, traceable, and easy to reason about. The cost is capped. All services depend on the orchestrator, and the orchestrator becomes a single point of complexity. In choreography, services react to events published by others. No central coordinator loses the coupling, but the overall flow is implicit and harder to trace. When a workflow breaks, you have to trace events across multiple handlers to find the failure. Neither is universally better. Orchestration for complex workflows with a clearer sequence. Choreography for loosely coupled event-driven pipelines. Question 12. Event-driven architecture. Services communicate by producing and consuming events rather than calling each other directly. Events are immutable records of something that happened. Order placed, payment processed. Producers publish to a broker like Kafka or Event Bridge. Consumers subscribe and react asynchronously. The broker is the durable store. Consumers can replay events. This gives you natural audit trails, temporal coupling, and horizontal scalability on the consumer side. Question 13. How do you ensure data consistency? 4 tools. Saga pattern, local transactions with compensating rollbacks, the outbox pattern, write your domain change, and the event do the same local transaction. A separate process publishes the event to the broker. This prevents dual write failures where the service commits but the event never gets published. Eventual consistency. Design your system to tolerate temporary stateless across services. And idempotent consumers processing the same event twice produce the same result. Question 10. The cap theorem. A distributed data store can guarantee at two most of 3 properties simultaneously. Consistency. Every read returns the recent write. Availability. Every request gets a response. Partition tolerance. The system operates despite network partitions. The network partitions are unavoidable in distributed systems. The real choice is between CP, consistent but potentially unavailable during a partition, and AP, available but potentially serving stale data. Hashbase and Zookeeper are CP. Cassandra and CouchDB are AP. The interview answer will be know which one your system is and be able to defend the choice against the use case. Question 14. Distributed tracing. A single request crosses multiple services. Without tracing, you cannot see where it spends its time or where it failed. Distributed tracing assigns a trace ID at the entry point. Each service adds a span, its segment of the journey. The tracing backend reconstructs the full path. Jaeger, Zipkin, AWS X-Ray, and Datadog are common tools. Tracing tells you which service is latency bottleneck, where errors originate in a multi-hop chain, and what your P99 looks like per service boundary. Question 15. Securing microservices. Validate identity at the API gateway using GWT or MTLS. Enforce authorization at the service level. The gateway is not enough. Between services, a mutual TLS so that each service presents a certificate and spoofing is prevented. Manage secret case with Vault or AWS Secret Manager. Never hardcode credentials. Rate limit at the gateway and use Kubernetes network policies or service mesh like Istio to restrict which services can communicate which. Question 16. What is the role of Docker and Kubernetes? Docker packages a service and its dependencies into a portable container image. Every environment, deployment, development, staging, production runs the same image. The works on my machine problem is gone. Kubernetes orchestrates those containers at scale. It schedules workloads onto nodes, health checks the running pods and restarts failed ones, scales horizontally on load, and rolls out new versions with zero downtime. The key abstraction, pod, deployment, service, ingress, config map, secret, those are the key abstractions. Together, Docker and Kubernetes are production runtime standard for microservices. If you are building microservices, you are building for container-based deployment. That is the masterclass. 18 questions, 5 pillars covered. The through line across all of them is the same. Every capability in distributed system has a cost. Independent deployment costs operational complexity. Decoupled communication costs eventual consistency. Resilience costs additional infrastructure. Know the trade-off, and you can answer any variant of those questions in an interview room. It's that easy. If this is useful for you, please subscribe for more senior engineering content and hit the like button. The full guide is linked in the description. Good luck out there. Thank you.